In the vast silence of the cosmos, every star, galaxy, and swirling nebula traces its origin back to a singular event, an unfathomable moment when existence itself was born. Before this turning point, there was no space to contain, no time to measure, and no matter to shape the structures we now see. What sparked the very first instant of creation? Was it a burst of unimaginable energy, a quantum fluctuation within an endless void, or something even more mysterious, something beyond our current grasp of physics? The story of the universe begins not with certainty, but with questions as ancient as the cosmos itself. With that said, let us begin. The concept of a first moment of creation is one of the most profound mysteries in science and philosophy. When we look into the night sky, we are not merely seeing stars, we are gazing back through time. Light from distant galaxies has traveled billions of years to reach us, acting like a cosmic archive, preserving the echoes of the past. This archive suggests that the universe was once far denser, far hotter, and infinitely more compact than it is today. Yet the true spark, the precise mechanism that transformed nothing into something, remains shrouded in enigma. The leading framework for understanding the universe's origin is the Big Bang model, but this term is often misunderstood. It does not describe an explosion in space, but rather the rapid expansion of space itself. Picture every point in the universe rushing away from every other point, not from a central location, but everywhere at once. This raises the fundamental question: what triggered this expansion? Did time itself begin in that instant, or was there a state before time that cannot be captured by conventional thought? Cosmologists have probed the earliest observable remnant of this event, the cosmic microwave background radiation. This faint afterglow, discovered in the mid-20th century, is a whisper from the universe's childhood, providing a snapshot of conditions about 380,000 years after the first spark. It shows remarkable uniformity, suggesting that the universe began in a state of extraordinary balance. But how did that balance come to be? Was it a result of physical laws emerging at creation, or did those laws exist timelessly, waiting for a universe to manifest them? To understand what may have sparked creation, one must venture into the realm of quantum physics and theoretical cosmology, where concepts like fluctuations, vacuum energy, and multiverse scenarios attempt to illuminate the darkness before time. Here, science walks a delicate line, balancing mathematical precision with deep speculation, for the closer we get to the beginning, the less our current theories can firmly grasp. When considering the origin of everything, one encounters the problem of the void. What does nothing truly mean? To the human mind, nothingness often conjures images of a vast, dark emptiness, a silent space devoid of matter. Yet this mental picture is still something. It has dimensions, depth, and silence. True nothing would have no space, no time, no potential, not even the possibility of emptiness. And yet, our universe exists, brimming with galaxies, stars, and energy. This paradox drives scientists and philosophers to search for what could ignite reality from non-reality. Some theories propose that the spark was not a creation from nothing, but rather a transformation. In the language of quantum mechanics, the vacuum is not truly empty. It teems with fleeting particles, constantly appearing and vanishing in unimaginably brief instants. This restless activity is known as quantum fluctuation. Could it be that our universe is the result of one such fluctuation that did not collapse back into nothing, but expanded, growing into the vast cosmos we observe today? This idea is not mere speculation, it has mathematical grounding. In certain models, the laws of physics permit the spontaneous emergence of energy from a vacuum, provided that the total balance remains zero. If positive energy, like matter and radiation, could be balanced by negative energy, such as gravity, then the net sum of the universe might still equal nothing. In this scenario, the universe is not something from nothing, it is nothing rearranged. Yet, even if this is true, it leaves another question unanswered. Where did the laws that allowed such a fluctuation come from? Did the principles of quantum physics exist timelessly, embedded in reality itself, or did they too emerge in the very first instant? Here lies one of the greatest mysteries of all, whether the laws of nature are eternal truths or products of creation themselves. Another attempt to explain the first spark draws from the concept of symmetry and its breaking. At the most fundamental level, the universe might have begun as a perfectly symmetrical state. Imagine a still pond, unbroken by ripples, smooth and undisturbed. In this primordial state, forces were unified: gravity, electromagnetism, and the strong and weak nuclear interactions may have been indistinguishable. Perfection ruled, and within perfection, nothing changed. But perfection cannot last forever. At some point, perhaps in a fraction of a second after the universe began, symmetry broke. Like cracks forming in ice as it cools, the forces of nature differentiated. Gravity split away, the strong force grew distinct, and the others followed, cascading into the physics we now observe. This breaking of symmetry released energy, driving rapid expansion and setting the stage for the formation of matter. In this sense, the spark of creation might not have been an event from outside the system, but rather the universe unfolding its own potential through instability. One theory that connects to this process is cosmic inflation. Proposed to explain the remarkable uniformity of the cosmos, inflation describes a period of exponential expansion, where the universe grew unimaginably large in an instant, far faster than the speed of light. This expansion smoothed out irregularities, spread energy evenly, and planted the seeds for galaxies to form billions of years later. Inflation raises intriguing implications. If the vacuum is unstable, inflation may not be a one-time event. Instead, it could occur repeatedly, creating countless universes, each with its own laws and constants. In this multiverse picture, our universe may simply be one bubble among an infinite cosmic foam. If so, then the first spark of our creation was not unique, it was one of many sparks, each igniting realities beyond our perception. The multiverse hypothesis forces us to confront an unsettling idea: perhaps our universe's birth was not inevitable, but accidental. In a sea of endless possibilities, universes could form with different configurations of matter, energy, and laws. Some may collapse instantly, others may expand into lifeless voids, while a rare few, like ours, unfold into structured, star-filled realms. If this is true, then the first spark of creation was not a singular miracle, but one roll of an infinite cosmic dice. But this perspective also deepens the mystery. If multiple universes exist, what lies beyond them? What provides the framework for universes to appear at all? Here, science edges into questions that border on the metaphysical. Some physicists argue that mathematics itself is the underlying reality, and that universes emerge wherever equations allow consistency. Others suggest there must be a deeper principle, a kind of primordial canvas upon which universes are painted. The cosmic microwave background, the afterglow of our universe's birth, provides some of the most compelling evidence for inflation and symmetry breaking. Within its faint patterns, scientists have detected tiny fluctuations, variations in temperature less than 1 part in 100,000. These subtle irregularities eventually grew into galaxies and clusters, shaping the very architecture of the cosmos. In their quiet imprint, we may glimpse the fingerprint of creation itself. And yet, these imprints do not tell us what preceded the spark. They tell us how the universe evolved after it began, but not what made it begin. This limitation is perhaps the most humbling aspect of cosmology. The deeper we peer into the past, the more the beginning recedes like a horizon, unreachable and veiled in mystery. Still, each discovery narrows the possibilities, guiding us closer to understanding what might have sparked the first moment of creation. To explore the first spark of creation, we must also confront the strange nature of time itself. Our ordinary experience of time flows like a river, carrying events from past to present to future. But if the universe had a beginning, does that mean time itself was created in that instant? Many models suggest exactly this, that time did not exist before the universe, because before has no meaning without time. This idea is deeply counterintuitive, for it asks us to imagine not a clock wound to zero, but a clock brought into existence altogether. Yet some theories hint at alternatives. Perhaps time is cyclical, with no true beginning or end, looping endlessly in phases of birth, expansion, contraction, and rebirth. In this view, what we call the first moment of creation might simply be one of countless previous cycles, hidden behind the veil of cosmic rebirth. If so, our universe may have inherited subtle imprints from its predecessors, echoes of earlier realities embedded in the cosmic fabric. Even within modern physics, there are proposals that challenge the absolute beginning. Some suggest that our universe could have emerged from a bounce, where a previous universe collapsed into extreme density before rebounding into a new expansion. Others propose that time itself is emergent, a property that arises only once matter and energy exist, like temperature emerging only when atoms interact. These ideas remind us that what we think of as linear time may only be a partial truth. Whether time was born in the spark of creation or stretches beyond our universe, it remains one of the most elusive elements in unraveling the origin of existence. To solve the mystery of the first moment, we must solve the riddle of time itself. Energy, too, holds a central role in this cosmic puzzle. The laws of physics as we know them declare that energy cannot be created or destroyed, only transformed. Yet if the universe emerged from nothing, where did all of its energy come from? One answer lies in the strange relationship between matter and gravity. Matter has positive energy, while gravity has negative energy. When combined, the total energy of the universe could, astonishingly, equal zero. In this sense, everything we see, the stars, the galaxies, the light, could be perfectly balanced by the pull of gravity, creating a universe that costs nothing at all. This concept reshapes the way we view creation. It suggests that the spark did not require an infinite reservoir of energy. It may only have required an imbalance, a quantum fluctuation within a sea of potential. Once expansion began, gravity and matter spread together, cancelling out in total, yet producing the rich and dynamic universe we inhabit. This balance also ties into the geometry of the cosmos. Measurements of the cosmic microwave background suggest that the universe is flat on the largest scales, meaning that its overall energy is extremely close to zero. This observation strengthens the idea that the cosmos could arise spontaneously, governed not by external input, but by the natural properties of energy itself. Still, while elegant, this view does not remove the ultimate question. If the universe can spring from nothing because energy balances to zero, what gives rise to the framework in which this balancing act can occur? It is as though we have discovered how the dice landed, but not where the dice themselves came from. Beyond energy and time lies the question of causality. In our everyday world, every effect has a cause. A seed grows into a tree because it was planted, a stone falls because gravity pulls it down. But when we trace causality back to the very first moment, we encounter a paradox. If everything requires a cause, then what caused the universe? And if something did cause it, then what caused that? The chain appears endless, leading us into infinite regress. Some theories propose that the first spark did not have a cause in the conventional sense. Instead, it may have been a spontaneous event, unbound by the rules that govern later reality. Quantum mechanics shows us that at the smallest scales, events can occur without deterministic causes. Particles can appear, disappear, or shift states unpredictably, governed only by probabilities. If causality itself breaks down at quantum scales, then perhaps the birth of the universe was such an event, an uncaused cause. Others propose that causality itself is emergent, arising only once the universe exists. In this sense, asking what caused the universe may be like asking what lies north of the North Pole, a question that assumes a framework where none applies. Yet this answer, while satisfying to some, leaves others uneasy. To declare that the universe had no cause feels incomplete, almost evasive. Perhaps the truth lies deeper still, in laws or realities beyond our current understanding. Perhaps the spark of creation was not without cause, but the nature of its cause is something our minds, bound by space and time, cannot yet grasp. At the heart of the question lies another profound mystery, the origin of the physical laws themselves. Our universe operates with remarkable consistency. Gravity pulls masses together, light travels at a constant speed, and matter interacts through specific forces. These laws are not optional, they define the behavior of everything that exists. Yet when we ask what sparked the first moment of creation, we must also ask, did these laws exist before the universe, or did they emerge alongside it? One school of thought imagines the laws of physics as timeless, like a hidden code underlying all possible realities. In this view, they were present even before the universe existed, waiting for a stage upon which they could act. When the spark ignited, it was not inventing laws but activating them, as though the rules were etched into reality itself. Another possibility is far more radical, that the laws were themselves born in that first moment, products of creation rather than its precursors. If this is true, then the universe could have begun in many different ways, governed by entirely different rules. Some universes might be filled with exotic forces, others might collapse instantly, and others might expand forever as silent voids. We inhabit one that allows complexity, structure, and continuity. This perspective often leads into the anthropic principle, the idea that we observe the universe as it is precisely because it permits observers to exist. Though controversial, it suggests that the spark of creation may not have favored life, structure, or galaxies deliberately, but rather that among countless possible sparks, we exist in one where conditions align. The question then deepens, are the laws necessary or contingent? Were they dictated by some ultimate reality, or do they shift across different possible universes? Until we can probe beyond our own cosmos, these remain open mysteries, hanging at the very edge of science and philosophy. Light itself carries part of the story of creation. The universe's first glow, the cosmic microwave background, was not just a faint afterglow but the first visible imprint of physical law taking shape. Before that time, the cosmos was a seething plasma of particles, too dense and hot for light to escape. Photons ricocheted endlessly off matter, unable to travel freely. Only when the universe cooled enough, hundreds of thousands of years after the spark, could atoms form and light journey unobstructed. That first light still travels today, stretched into microwaves by the expansion of space, whispering to us about the conditions of the early cosmos. What makes this radiation remarkable is its uniformity. Across the sky, it is nearly the same temperature, varying only slightly in subtle patterns. These faint variations tell us that the early universe was astonishingly smooth, with only tiny fluctuations, seeds that would one day grow into galaxies and clusters. Without those fluctuations, the universe would remain a featureless sea, devoid of structure. The origin of these tiny irregularities may hold clues to the spark itself. Quantum theory suggests that fluctuations at the smallest scales can be magnified by cosmic inflation, stretched across the expanding fabric of space to become the seeds of galaxies. If so, then the first light we see today is, in a sense, a magnified image of quantum events at the birth of creation. Studying the cosmic microwave background has become one of the most powerful tools in cosmology. By analyzing its patterns, scientists can infer not only the density and composition of the early universe but also hint about what may have driven its initial expansion. Each faint ripple is a frozen memory of creation, encoded in light that has traveled for billions of years. As we look deeper, matter itself becomes a mystery tied to the first spark. For every particle of matter, there should also exist an antiparticle, identical in mass but opposite in charge. When matter and antimatter meet, they annihilate one another, leaving behind pure energy. According to the known laws of physics, the early universe should have produced matter and antimatter in equal amounts. If that were true, they should have destroyed each other completely, leaving behind only radiation. Yet our universe is dominated by matter. Stars, planets, and life exist because, somehow, matter triumphed over antimatter. This imbalance, called baryon asymmetry, is one of the great unsolved puzzles of cosmology. The spark of creation must have contained within it the conditions for this imbalance, tipping the scales slightly toward matter. Even the tiniest excess, perhaps just one extra particle of matter for every billion pairs, would have been enough to ensure a universe of stars and galaxies. But what caused that tiny preference? Some theories suggest that during the earliest instance, as forces separated and symmetry broke, the laws of physics allowed matter to gain a slight edge. Subtle violations of symmetry in particle interactions could have introduced the imbalance. Experiments today search for these violations, hoping to uncover the fingerprints of creation in the tiniest behaviors of subatomic particles. The presence of matter over antimatter is, in itself, evidence that the spark of creation was not perfectly balanced. It had direction, asymmetry, and consequence. Without this imbalance, there would be no galaxies, no suns, no worlds. The very existence of matter speaks of a profound event woven into the first moment, one whose origin still eludes complete explanation. The spark of creation also gave rise to one of the universe's most dominant but least understood components, dark matter. Though invisible, its presence shapes the cosmos on every scale. Galaxies spin too fast to be held together by visible matter alone. Clusters of galaxies bend light in ways that betray unseen mass. These observations point to dark matter, an enigmatic substance that neither emits nor absorbs light, yet outweighs ordinary matter 5 to 1. But what role did dark matter play in the earliest moments? Without it, galaxies might never have formed. In the young universe, dark matter provided the gravitational scaffolding into which ordinary matter could fall, gathering into clouds that would ignite into stars. If the spark of creation had not included dark matter, the universe may have remained a diffuse mist of particles, never coalescing into structures. Yet the true nature of dark matter remains hidden. Is it composed of undiscovered particles, relics of creation itself? Could it be a manifestation of deeper laws that transcend our current physics? Some theories even suggest dark matter may link to other dimensions, its effects spilling into our universe while remaining invisible to our instruments. If so, dark matter is not just a product of the spark but a messenger from realms beyond, hinting that creation was richer and stranger than we imagine. In the cosmic story, dark matter is the silent architect, shaping galaxies and clusters, ensuring that the universe did not remain empty but grew into the vast structures we now observe. Its presence suggests that the spark of creation was not random, but finely tuned to produce complexity. Alongside dark matter lies its mysterious twin, dark energy. Where dark matter pulls, binding galaxies together, dark energy pushes, driving the cosmos apart. It is the name given to the unknown force responsible for the accelerating expansion of the universe, a discovery that shocked astronomers in the late 20th century. Instead of slowing under gravity, the universe's expansion has been speeding up, as if some invisible pressure pervades the vacuum of space. This raises profound questions about the first spark. Did dark energy exist from the very beginning, woven into the fabric of space-time itself? Or did it emerge later, as the universe evolved, like a hidden reservoir slowly revealing its influence? If it was present from the start, then dark energy may have shaped the earliest expansion, perhaps even playing a role in the inflationary burst that set the cosmos on its path. One leading explanation ties dark energy to the quantum vacuum, the restless sea of fluctuations at the foundation of reality. If so, then the same phenomenon that may have sparked creation also drives its ongoing expansion. The first instant and the present are linked, bound by the same mysterious force. Yet the magnitude of dark energy is puzzling. Calculations based on quantum theory predict a value vastly larger than what is observed, so large that the universe would have torn itself apart instantly. Why the true value is so small, yet not zero, is one of the greatest unsolved riddles in physics. Some suggest that only in a universe with such a value could galaxies and stars form, making our existence possible. If this is correct, then dark energy is not just a cosmic afterthought but part of the initial spark, a quiet, invisible hand guiding the universe from its birth to its future. The structure of the universe is another clue to its origin. On the grandest scales, galaxies are not scattered randomly, but woven into vast filaments, stretching across space like threads in a cosmic web. Between these filaments lie immense voids, regions nearly empty of matter. This large-scale architecture arose from the tiniest fluctuations present at creation, amplified by gravity over billions of years. Simulations of cosmic evolution, using supercomputers and the laws of physics, have revealed how this web might have emerged. Beginning with a nearly uniform universe, small differences in density, perhaps seeded by quantum fluctuations in the first instant, grew as matter fell into denser regions. Over time, these clumps stretched into filaments, creating the interconnected structure we see today. The cosmic web is, in essence, the frozen fingerprint of the spark, magnified to galactic scales. What makes this structure even more fascinating is its similarity to patterns in entirely different systems, neural networks, river basins, even the distribution of energy in turbulence. These echoes suggest that the same mathematical principles may govern complexity across nature, from the smallest scales to the largest. If the universe's web reflects universal laws, then the spark of creation may not have been chaos but order unfolding through hidden patterns. Observations of the cosmic web also allow us to test theories of the universe's origin. By comparing the distribution of galaxies with predictions from inflation, dark matter, and dark energy, scientists can refine their understanding of what the spark must have been like. In every filament and void lies a clue, each structure a reminder that the cosmos is not random, but shaped by deep principles encoded in its first moment. As we press closer to the first spark of creation, we encounter the concept of singularity. In classical general relativity, tracing the expansion of the universe backward in time leads us to a point of infinite density and zero volume. At this singularity, the known laws of physics collapse, unable to describe conditions of such extremity. But is this singularity a real feature of the cosmos, or merely a sign that our theories are incomplete? Many scientists suspect the latter. Singularities are red flags, indications that mathematics is being pushed beyond its limits. Just as Newton's laws fail at near light speeds, general relativity may fail at the moment of creation, where quantum effects dominate. To truly understand the first spark, we need a theory that unites general relativity with quantum mechanics, a framework often referred to as quantum gravity. Various approaches attempt this unification. String theory, for instance, envisions fundamental particles not as points but as vibrating strings, their harmonics giving rise to different forces and particles. In this view, the early universe might not have been a singularity at all but a compact, multidimensional state where strings interacted in ways that sparked expansion. Another contender, loop quantum gravity, suggests that space-time itself is quantized, composed of tiny discrete units. If so, the universe could not shrink into a singularity, but instead bounce from a previous phase of contraction. Whether through strings, loops, or another yet undiscovered framework, the resolution of singularities may reveal that the first spark was not an abrupt beginning from nothing, but a transition, a bridge from a hidden reality into the cosmos we know. The role of dimensions is another intriguing path to explore when asking what sparked creation. Our universe appears to operate with 3 dimensions of space and 1 of time, but modern theory suggests there may be more. String theory, for example, requires additional spatial dimensions, perhaps 6 or 7 more, curled up so tightly that they are invisible to us. If such dimensions exist, they may have been crucial in the first instant. Some models propose that the universe began when higher dimensional membranes, or brands, collided. This collision would have unleashed energy on a colossal scale, igniting the expansion of space-time. In this view, our entire cosmos is the byproduct of interactions in a reality far larger and richer than what we perceive. Other ideas suggest that additional dimensions could explain why gravity is so weak compared to other forces. If gravity leaks into extra dimensions, then the balance of forces in the early universe may have been shaped by unseen geometries. The spark of creation may thus not only be an event in our 4-dimensional realm but a ripple through a deeper, multidimensional reality. The possibility of hidden dimensions stretches our imagination, but it also offers testable predictions. Subtle signatures in the cosmic microwave background, or in the behavior of high-energy particles, might one day reveal their presence. If confirmed, such findings would transform our understanding of the spark, showing that what we call the beginning was merely the visible edge of a far greater and more complex tapestry. Another mystery tied to the spark of creation is entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy increases over time. This principle explains why energy spreads, why stars burn out, and why the universe tends toward greater disorder. But if entropy always rises, then the first moment of creation must have begun in a state of incredibly low entropy, astonishingly ordered and finely tuned. This fact is puzzling. Why would the universe start in such an improbable state? A high-entropy beginning would have been far more likely, yet it would not have produced the structures we observe today. Instead, the universe began with just the right conditions for galaxies, stars, and complexity to emerge. Some propose that inflation provides the answer. By stretching space to vast scales, inflation could have smoothed irregularities, effectively resetting the entropy of the cosmos to a uniform, low state. Others argue that the low entropy beginning demands a deeper explanation, perhaps pointing to a principle beyond current physics. The enigma of entropy also connects to the arrow of time. The fact that time seems to move from past to future, that we remember yesterday but not tomorrow, is tied to entropy's growth. If the universe began in a low entropy state, then the direction of time itself was set at the spark of creation. In this sense, the first instant not only created space and energy, it created the very flow of time as we experience it. The mystery of fine-tuning arises naturally when we speak of the first spark of creation. The universe appears to be delicately balanced in ways that allow stars, galaxies, and complexity to exist. The strength of gravity, the charge of the electron, the speed of light, the density of dark energy, all these values fall within narrow ranges. If they had been even slightly different, the cosmos might have collapsed upon itself, expanded into emptiness, or remained sterile and lifeless. This raises a profound question: why are the constants of nature what they are? Was this balance inevitable, written into the fabric of existence, or was it the outcome of chance? Some scientists argue that the apparent fine-tuning is explained by the multiverse. If countless universes exist, each with different values, then we naturally find ourselves in one of the rare universes that permits complexity. Others suggest that the fine-tuning reflects deeper laws not yet discovered, laws that determine these constants as necessary outcomes rather than arbitrary accidents. There is also the possibility that fine-tuning is only an illusion. Perhaps what we perceive as improbable is simply the only way reality can exist. Still, the fact remains: the universe's parameters are remarkably suited to allow structure and order. From the balance of forces that shaped atoms, to the expansion rate that set galaxies into motion, every detail seems aligned. If fine-tuning is real, then the first spark of creation was not merely the ignition of existence but the precise arrangement of its rules. It suggests that the beginning was not chaotic, but deeply ordered, an opening act in which the very stage of reality was calibrated to allow the drama of the cosmos to unfold. Symmetry and its breaking also carry echoes of artistry in the story of creation. At the dawn of time, the universe may have been a perfect balance, where forces and particles were indistinguishable. Yet this perfection was unstable. Small instabilities caused symmetries to break, differentiating the four fundamental forces and creating distinct particles. In this sense, creation may not have been a single act, but a cascade of transitions, each one unlocking new possibilities for structure. Physicists liken this process to phase transitions in matter. Water, for instance, transforms from liquid to ice when conditions change. Similarly, the early universe may have undergone phase transitions as it cooled, with forces crystallizing out of unity-like patterns in frozen water. Each step of symmetry breaking released energy, shaping the conditions of expansion and scattering the seeds of matter into the cosmos. One of the most fascinating aspects of symmetry breaking is that it leaves behind relics, cosmic fossils imprinted in space-time. Hypothetical structures like cosmic strings, domain walls, or monopoles may have formed in the earliest instance. If such relics exist, they could carry information about the conditions of the spark, preserved for billions of years. Detecting them would be like finding ancient inscriptions on the walls of the cosmos, offering direct evidence of how creation unfolded. Though none of these relics have yet been confirmed, their possibility reminds us that the first spark may have left behind more than radiation. It may have etched signatures into the very geometry of space-time itself, waiting for us to uncover them. The search for gravitational waves has opened another window into the first instant of creation. Unlike light, which interacts with matter and can be scattered or absorbed, gravitational waves are ripples in space-time itself. They travel almost unimpeded across the cosmos, carrying pristine information from the events that produced them. While we have already detected gravitational waves from colliding black holes and neutron stars, scientists hope to one day detect the faint background of waves generated during the universe's birth. If inflation occurred, it should have produced a distinct signature of gravitational waves. These primordial ripples would have stretched space-time during the universe's earliest expansion, leaving behind patterns in the cosmic microwave background's polarization. Detecting such signals would provide direct evidence of processes that occurred less than a trillionth of a second after the spark. Though these primordial waves remain elusive, the search continues with increasing precision. Each new experiment brings us closer to glimpsing the very vibrations of creation itself. Imagine being able to listen not only to the afterglow of the universe's birth but to its first tremors, the echoes of space-time shaking as existence itself took form. Such a discovery would not only confirm theories of inflation but also provide a rare glimpse into the physics beyond our current reach. It would bridge the gap between what we infer and what we can measure, turning speculation about the spark of creation into tangible evidence. Until then, the silence of gravitational waves keeps the first instant hidden, like a secret locked within the fabric of space-time. The possibility of a cyclical universe has fascinated thinkers for centuries. Instead of a single spark marking the absolute beginning, perhaps creation is part of an eternal rhythm, expansion, contraction, and rebirth. In this view, the universe may one day slow its expansion, collapse inward under gravity, and reach a dense state before bouncing outward again in a new Big Bang. Each cycle would erase most traces of the previous one, yet subtle imprints might survive, encoded in the geometry of the cosmos. Modern cosmology has revisited this idea through models such as the ekpyrotic universe, which draws from higher dimensional physics. According to this concept, our universe could be the product of two higher dimensional brands colliding, triggering expansion. After trillions of years, the process could repeat, with universes sparking endlessly from such encounters. A cyclical view raises profound questions. If the cosmos has no ultimate beginning, then what we call the first spark may have been preceded by countless others. Creation would not be a singular event but an infinite cycle, with universes rising and falling like waves on an endless ocean. While evidence for a true bounce remains speculative, some patterns in the cosmic microwave background might hint at anomalies, echoes of earlier cycles. If confirmed, they would challenge the idea of a unique beginning and instead suggest that creation itself is woven into an eternal process of renewal. The quantum realm offers perhaps the most perplexing hints about creation. At the smallest scales, particles do not behave like solid objects but like probabilities, existing in superpositions until observed. Energy can fluctuate into existence, particles can tunnel through barriers, and uncertainty reigns as a fundamental property of reality. This leads to the provocative idea that the universe itself may have emerged as a quantum fluctuation. In quantum theory, empty space is never truly empty, it seethes with activity, with particles appearing and vanishing in fleeting instants. Most fluctuations cancel themselves out, but what if, under certain conditions, one fluctuation expanded rather than collapsed? That single event could have blossomed into the cosmos we see today. Such a scenario aligns with the concept of a zero-energy universe, where the positive energy of matter is balanced by the negative energy of gravity. If this balance holds perfectly, then the birth of the universe may have required no external input at all. Reality, in this sense, could have emerged spontaneously, governed only by quantum uncertainty. However, the quantum fluctuation model also raises questions. What defines the stage on which fluctuations occur? What gives rise to the rules of quantum physics in the first place? If they existed before the universe, then what kind of reality contained them? If they were born with the spark, then what mechanism allowed them to manifest? The mystery deepens, leaving us at the boundary where science blurs into philosophy. Beyond quantum fluctuations lies the possibility of a multiverse, an ensemble of countless universes, each with its own conditions, laws, and perhaps even dimensions of time and space. In this vast landscape, the spark of our creation would not be unique but one among innumerable beginnings, each flickering into existence from deeper realities. One framework for this concept is eternal inflation. If inflation is not a one-time burst but a continuing process, then different regions of the greater cosmos could undergo expansion at different times. Each region that stops inflating would form its own bubble universe, isolated from others by the vastness of spacetime still expanding between them. Our universe would then be one bubble in a frothing multiversal sea. This scenario explains fine-tuning in a natural way. If universes are born with varying constants, then only some will support galaxies, stars, and complexity. We find ourselves in one of those rare bubbles not because it was chosen, but because only such bubbles can give rise to observers. Yet the multiverse remains controversial. By definition, regions beyond our cosmic horizon cannot be observed directly. Evidence might only appear indirectly, perhaps through faint imprints of collisions between bubble universes or anomalies in the cosmic microwave background. Until such evidence is found, the multiverse remains both a tantalizing explanation and a philosophical leap, an attempt to explain the spark of creation by multiplying the sparks without limit. Space-time itself is central to the question of the first spark. In Einstein's general relativity, space and time are not separate arenas but part of a single fabric, stretching, bending, and curving under the influence of mass and energy. The expansion of the universe is not galaxies moving through space, it is space itself growing between galaxies. But if spacetime itself was created in the first instant, then the spark was not just the birth of matter and energy, it was the birth of the very arena in which existence unfolds. This challenges our ability to imagine before the universe. If time itself began with the spark, then there was no before, only a timeless state beyond comprehension. Some models suggest that spacetime is emergent, much like temperature emerges from atoms in motion. In this view, the first spark may have been the phase transition that brought spacetime into being, condensing it from a deeper, pre-geometric reality. The idea of emergent spacetime also links to entanglement in quantum mechanics. Some physicists propose that the connectivity of space itself may arise from quantum entanglement, the mysterious link between particles across vast distances. If so, then the spark of creation was not merely the ignition of energy, but the sudden emergence of an interconnected network, the geometry of reality itself born from quantum bonds. To understand the first instant, then, is not only to understand matter, energy, and light, but to grasp the origin of the stage upon which all events take place. The universe did not appear in space and time, it brought space and time into existence with it. Another avenue of exploration concerns the role of symmetry at cosmic scales. The observable universe, when viewed broadly, appears remarkably uniform. Galaxies are spread evenly, the cosmic microwave background is smoothed to extraordinary precision, and the laws of physics seem identical everywhere. This uniformity suggests that the spark of creation produced a cosmos with a high degree of order. Yet on smaller scales, the universe is anything but uniform. Galaxies cluster into filaments, stars explode into supernovae, and planets form with intricate variation. This duality, smoothness on large scales, complexity on small scales, may be a direct result of how the spark unfolded. Inflation, by stretching space rapidly, smoothed irregularities, while quantum fluctuations introduced tiny imperfections that seeded later complexity. This interplay between uniformity and imperfection is essential. Without large-scale smoothness, the universe would be chaotic and inhospitable. Without small-scale variations, it would be featureless and barren. The spark of creation achieved a delicate balance, laying the groundwork for both order and diversity. Interestingly, this pattern mirrors principles found in many natural systems. From the branching of trees to the flow of rivers, complexity often arises from simple rules interacting with slight imperfections. The first spark may have encoded this principle into the cosmos itself, showing that creation was not a rigid act of uniformity, nor a descent into chaos, but the harmonious blending of both. As we unravel the mysteries of creation, we confront the limits of human understanding. The spark that began the universe occurred at energies and densities far beyond anything we can replicate in laboratories. Our largest particle accelerators, while powerful, only scratch the surface of the conditions present in the first fractions of a second. This gap forces us to rely on theory, mathematics, and indirect evidence, piecing together a picture from the cosmic afterglow and the structure of the universe today. Yet this challenge also drives innovation. Theories of quantum gravity, multidimensional models, and ideas of emergent spacetime are all attempts to reach beyond those limits. Each is speculative, but each pushes the boundaries of knowledge, forcing us to imagine realities far stranger than our everyday world. The search for the first spark is not merely about answering a question of beginnings, it is about probing the deepest foundations of reality. What we discover may redefine not only how we view the cosmos, but what we mean by existence itself. Perhaps the spark was not a single moment at all, but a process unfolding across layers of reality we have only begun to glimpse. Whatever the answer, the pursuit of the first moment of creation reminds us of the scale of our ignorance and the vastness of the mystery. The fact that we can even ask such questions is remarkable. And though the ultimate answer remains hidden, every new discovery brings us closer to illuminating the origins of the universe. The earliest stages of creation may have also produced exotic forms of matter and energy that no longer exist today. Physicists speculate that shortly after the spark, the universe contained particles far heavier and stranger than those we now observe. These primordial entities may have decayed rapidly, leaving only traces in the form of cosmic background radiation, gravitational waves, or the balance of matter and antimatter. Among these possibilities are hypothetical particles like magnetic monopoles, objects carrying a single magnetic charge instead of the usual north and south poles. Others imagine relics of supersymmetry, a proposed extension of physics where every known particle has a heavier partner. Such particles could account for dark matter, linking the mystery of creation to the invisible scaffolding of the cosmos. The existence, or absence, of such relics could tell us much about the nature of the spark. If they are found, they would provide direct evidence of the exotic physics that dominated the universe's earliest fractions of a second. If not, then the spark may have followed a simpler path, smoothing away such phenomena through inflation or other mechanisms. Either way, the possibility of lost particles reminds us that the first moment was a laboratory unlike any we can build, operating at energies we can only dream of. To probe it is to attempt to recreate the universe itself in our minds, guided by mathematics, observation, and the faint traces left across the cosmos. The notion of the vacuum plays a central role in theories of the spark. To everyday intuition, a vacuum is empty space, nothingness. But in quantum physics, the vacuum is a restless sea, filled with fleeting fluctuations and virtual particles. This activity, invisible to the eye, has measurable effects, such as the Casimir effect, where two plates placed close together experience a force from the vacuum itself. If the vacuum is truly alive with energy, then perhaps the spark of creation was triggered by a transformation of this energy. Inflationary theory, for example, posits that a false vacuum state, an unstable configuration of this quantum sea, suddenly decayed, releasing its stored energy in a burst that drove expansion. The universe, in this picture, was born from a phase transition in the vacuum itself. This raises a fascinating possibility: the universe may not be a one-time anomaly but a natural outcome of vacuum dynamics. If the vacuum can produce universes under the right conditions, then creation could be an ongoing process, happening not only once but continuously across an infinite backdrop of possibilities. Still, questions remain. What defines the rules of the vacuum? Why does it exist at all? Is it eternal, or did it too require a spark? The deeper we look, the more the vacuum appears less like nothingness and more like a hidden reservoir, holding the potential for everything that is. Symmetry, entropy, energy, vacuum, all these ideas converge on a single realization: the spark of creation may not be fully understandable in human terms. Our language is built on comparisons, metaphors, and everyday experience, yet the first instant of the cosmos is unlike anything else. It is a frontier where time, space, and causality themselves are transformed. This challenge does not mean the pursuit is futile. On the contrary, it may force us to expand the limits of imagination and develop new ways of thinking. Throughout history, revolutions in science have come when old assumptions were overturned, when the Earth was no longer the center, when time and space became relative, when matter dissolved into quantum uncertainty. The spark of creation may demand an even greater shift, one that redefines existence itself. Some philosophers argue that asking what sparked creation may be the wrong question altogether. If time began at the spark, then there was no before. The universe did not ignite like a flame struck from flint, it unfolded as the natural condition of reality. The spark, then, may not be an external cause but the self-emergence of existence. Whether through physics, mathematics, or philosophy, the search for the origin of everything reminds us that the universe is not only vast in space but profound in mystery. The spark of creation is not merely a point in time, it is the threshold where comprehension falters, and awe begins. Another path to understanding the spark of creation lies in the study of black holes. These enigmatic objects, formed from collapsed stars, compress matter into such density that not even light can escape. In many ways, they echo the conditions thought to exist at the universe's birth: extreme density, warped space-time, and horizons beyond which we cannot see. By studying black holes, we may catch glimpses of the physics that ruled the first instant. One of the most intriguing parallels is the concept of a singularity. At the heart of a black hole, general relativity predicts infinite density and a breakdown of known physics, much like the singularity predicted at the beginning of the universe. If we can resolve the paradoxes of black holes, how information behaves, how quantum mechanics and gravity reconcile, we may also unlock the mysteries of the first moment. Hawking radiation, though not to be mentioned in name here, suggests that black holes are not entirely black. They may slowly evaporate, releasing faint radiation at their event horizons. This idea bridges quantum mechanics and gravity, offering hints of a deeper theory. If horizons can give rise to radiation, then perhaps the horizon of the first instant also held secrets, releasing the universe itself from an initial boundary. In this way, black holes serve as natural laboratories. They show us that extreme conditions force the union of the greatest theories of physics, and that in their reconciliation may lie the key to the spark of creation. What we learn from their depths could illuminate the beginning of all things. Cosmologists also look to the earliest chemical signatures for evidence of the spark. The lightest elements, hydrogen, helium, and traces of lithium, were forged in the furnace of the early universe, within the first minutes after the Big Bang. This process, known as primordial nucleosynthesis, is one of the most direct pieces of evidence for how the universe began. According to theory, as the universe cooled from its searing initial temperatures, protons and neutrons combined to form the first atomic nuclei. The exact proportions of these elements, about 75% hydrogen, 25% helium, and a trace of lithium, match predictions almost perfectly. This agreement between theory and observation is a cornerstone of modern cosmology, confirming that the spark set the stage with remarkable precision. Yet this precision also raises questions. Why did the universe cool at exactly the right rate for atoms to form? Why were the proportions so finely balanced? If conditions had been slightly different, the cosmos might have been dominated by heavy elements or remained a featureless sea of hydrogen, preventing the formation of stars and planets. Primordial nucleosynthesis shows us that the spark was not just about creating energy, it was about guiding energy into form. It transformed chaos into order, producing the ingredients for everything that followed. From the simplest atoms came stars, from stars came heavier elements, and from those elements came planets and life. The spark of creation was not only the birth of space-time but also the first act of chemistry. The cosmic horizon presents another profound limit to our understanding of the first moment. No matter how powerful our telescopes, we can only see as far as light has had time to travel since the spark. This defines the observable universe, a sphere around us nearly 46 billion light-years in radius. Beyond this horizon lies the unobservable, hidden forever unless new physics allows us to pierce the veil. This boundary reminds us that our picture of creation is incomplete. The universe we see may be only a fraction of the whole, a small patch in a far vaster reality. Inflation theory suggests that the true cosmos may be unimaginably larger, stretching far beyond the horizon, perhaps even infinite. If so, our observations capture only a local fragment of the story, leaving the greater context unknown. The horizon also raises the question of what it means to speak of the whole universe. If we cannot see beyond it, is the rest real, or is it only a mathematical necessity? Some argue that what lies beyond the horizon is no less real than what lies within, just as the lands beyond a mountain are real even if unseen. Others contend that unless it can be observed, it remains speculative, part of philosophy more than science. Still, the cosmic horizon humbles us. It tells us that even as we peer into the depths of creation, there are limits to what we can know. The spark of creation may remain partly hidden, always just beyond our reach, reminding us that the universe is not only a source of knowledge but of enduring mystery. One of the deepest puzzles tied to the spark of creation is the nature of quantum entanglement. At the smallest scales, particles can become mysteriously linked, so that the state of one instantly influences the state of another, no matter how far apart they are. This phenomenon, confirmed by countless experiments, defies ordinary notions of locality and causality. Some theorists propose that entanglement may not simply be a curious feature of quantum mechanics, but the very fabric from which spacetime itself is woven. If true, then the spark of creation was not merely the birth of matter and energy, but the sudden emergence of an entangled network. In this picture, reality itself is held together by invisible quantum threads, and the geometry of space arises from their connections. This idea also touches on the famous paradox of black holes, how information can seemingly vanish when matter crosses an event horizon. If entanglement is the foundation of space-time, then information is never truly lost, it is encoded in the web of quantum links. The same principle may apply to the beginning of the universe. The information of creation could still be preserved, written into the entanglement structure that defines reality. Entanglement thus provides a radical possibility. That the spark of creation was not a singular explosion but the weaving of a cosmic tapestry, a sudden network of correlations binding everything into a coherent whole. If so, the universe is not simply a collection of objects in space, but a vast, interconnected system where separation is an illusion, and the spark itself was an act of universal connection. The mathematics of creation also inspires awe. Equations such as Einstein's field equations or the principles of quantum field theory are not arbitrary inventions but precise descriptions of how reality behaves. These mathematical structures often predict phenomena long before they are observed, as though the universe itself is written in code. This raises the question, are the laws of mathematics discovered or invented? If the spark of creation followed mathematical rules, then those rules must have existed in some form prior to the universe itself. They may be eternal truths, not dependent on the cosmos, but fundamental to reality at its deepest level. In that case, the spark was the moment when mathematics became physics, when abstract law became embodied as energy and matter. Others suggest that mathematics only appears fundamental because it is the language we use to describe patterns. If another form of intelligence existed, it might conceive of reality in entirely different terms. Yet the remarkable effectiveness of mathematics cannot be denied. It describes galaxies, particles, and the expansion of space with astonishing accuracy. The role of mathematics in the spark of creation is both a scientific and philosophical mystery. If equations exist timelessly, then the spark may have been their realization. If not, then mathematics itself may have emerged with the universe, part of the structure born in that first instant. Either way, the relationship between numbers and reality is one of the most profound mysteries of the cosmos. The arrow of time remains inseparable from the question of the first spark. Why does time flow in one direction, from past to future, rather than both ways? The answer seems tied to entropy, which increases as the universe evolves. Yet this raises a deeper question: why did the universe begin in a state of such low entropy that time's arrow could be set at all? If the cosmos had begun in high entropy, time might have had no preferred direction, and events would have unfolded without order. Instead, the first spark produced a cosmos primed for change, evolution, and history. Every star that shines, every galaxy that forms, every story that unfolds is possible only because of the asymmetry embedded at the start. Some theorists propose that the arrow of time is not absolute but local. In a larger multiverse, time might flow differently in other regions, or even reverse under exotic conditions. If so, then the spark of creation did not simply set one universal arrow but created the conditions for diverse temporal flows across a greater reality. Others argue that time itself may be emergent, like a property of entanglement or thermodynamics. If true, then the spark was not simply the beginning of time, it was the creation of the very conditions that make time possible. In this sense, the universe did not just begin, it began to begin, unfolding the possibility of sequence, memory, and change. The first spark of creation also forces us to confront the question of cause and effect at the deepest level. In daily life, causality is unquestionable, events follow from other events. Yet at the beginning of the universe, this principle may no longer apply. If time itself began at the spark, then causality, which depends on time, could not exist before it. In this sense, the universe might not have been caused in any traditional sense, it may simply have arisen. Quantum mechanics reinforces this perspective. At the smallest scales, events occur without strict determinism. A particle may appear, decay, or shift states not because of an identifiable cause, but as a manifestation of probabilities. The birth of the universe could have been a quantum event on the grandest scale, a spontaneous fluctuation that required no precursor. Still, some physicists are unsatisfied with this view. They argue that even if the universe was born from a quantum fluctuation, the rules of quantum physics themselves demand explanation. Why do probabilities exist? Why do they operate as they do? What framework allowed the fluctuation to occur? These questions push us to the edge of science and into philosophy. Perhaps causality itself is emergent, just as time may be. In the deepest reality, there may be no why at all, only existence, unfolding according to principles we cannot yet grasp. The spark of creation, then, may have been the moment when cause and effect themselves were born, rather than the result of an earlier chain of causes. The interplay between order and chaos also defines the spark of creation. On one hand, the cosmos appears finely tuned, its constants balanced with exquisite precision. On the other, quantum uncertainty and randomness lie at its foundation. How could both order and chance emerge from the same beginning? One possibility is that the universe began in a state of maximum simplicity, a uniform, smooth condition with minimal information. As it expanded, quantum fluctuations introduced randomness, creating slight variations. Over time, these tiny imperfections grew into galaxies, stars, and planets. In this way, complexity arose not from initial chaos, but from the dance between order and fluctuation. This process mirrors patterns seen in other natural systems. Snowflakes, for example, grow from simple crystalline rules but gain complexity through environmental variations. Similarly, the cosmos may have emerged from simple initial rules, with randomness shaping its intricate details. The spark of creation may have encoded both the laws of order and the seeds of unpredictability, ensuring a universe that is neither sterile nor chaotic, but balanced between the two. This balance may also explain why the universe is comprehensible. If it were purely random, no consistent patterns would exist to study. If it were purely ordered, it might lack diversity and richness. Instead, the first spark produced a cosmos in which order frames the stage, and chance writes the script. The geometry of the universe also traces back to the spark of creation. Observations suggest that the cosmos is remarkably flat, meaning that parallel lines remain parallel on the largest scales, and the overall curvature of spacetime is close to zero. This is surprising, because without precise initial conditions, the universe would quickly curve into either collapse or runaway expansion. Inflationary theory provides an elegant solution. By stretching spacetime exponentially in its earliest moments, inflation would have driven the universe toward flatness, erasing any initial curvature. The remarkable flatness we observe today may therefore be a direct consequence of the spark's earliest processes. Yet this explanation invites further questions. Why did inflation occur at all? What triggered it, and what caused it to end? The flatness of the universe is evidence that inflation may have taken place, but the mechanism behind it remains speculative. Some models suggest that a field of energy, often called the inflaton, drove inflation. If so, then the first spark may have been the moment this field shifted state, unleashing expansion. Flatness also relates to the universe's fate. If the cosmos is truly flat and dominated by dark energy, it may expand forever, with galaxies drifting farther apart until they vanish beyond one another's horizons. In this sense, the geometry of the universe is not just a clue to its beginning, but also a window into its ultimate destiny, both written in the same spark. The concept of horizons provides yet another layer to the mystery of the spark. Beyond the cosmic horizon, the furthest distance from which light has reached us, lies an unobservable realm. But there are also other horizons, defined not by distance but by the limits of physics itself. One of these is the Planck scale, the smallest unit of space and time that current theories can meaningfully describe. At the Planck scale, about 10^35 10⁻⁻35, 10^35 meters, quantum fluctuations of spacetime itself become significant. Distances blur, time intervals fluctuate, and the smooth geometry described by relativity dissolves into a frothing quantum foam. It is at this scale that the spark of creation is thought to have occurred. Unfortunately, the Planck realm is far beyond the reach of current experiments. No particle accelerator can probe it, no telescope can see it. We are left with mathematics, inference, and imagination to guide us. String theory, loop quantum gravity, and other candidates for a theory of everything aim to describe what happens at this frontier. Each offers different possibilities. Vibrating strings, discrete loops, or even networks of information as the true substrate of reality. If we could peer into the Planck scale froth, we might witness the spark itself, space-time bubbling into existence, laws condensing from the chaos, and energy bursting forth from the vacuum. Until then, the Planck horizon remains a veil over the very birth of the cosmos, an invisible boundary separating what we know from the ultimate mystery of creation. The spark of creation also invites us to think about the role of symmetry at the deepest levels of reality. Physicists believe that at unimaginably high energies, the fundamental forces of nature may have been unified into a single interaction. As the universe cooled, this symmetry broke, separating into gravity, electromagnetism, and the nuclear forces. If this grand unification is correct, then the spark of creation was a moment of symmetry so perfect that it contained within it the potential for all diversity. Like a crystal shattering into pieces, the breaking of symmetry released energy and differentiated the forces, enabling complexity to arise. Yet this idea leads to deeper questions. Why does symmetry break? What determines how it breaks? Could it have broken differently, producing universes governed by completely alien laws? Some models suggest that in other possible realities, forces could be stronger or weaker, atoms unstable, or chemistry impossible. Our universe may be just one outcome of a far broader landscape. Experiments in particle physics continue to search for hints of unification. Collisions at high energies may reveal particles predicted by unified theories, remnants of the symmetry that existed at the spark. If discovered, they would provide direct evidence of how the forces we know today first separated, illuminating the earliest chapters of cosmic history. The spark, then, may not have been a random flash, but the unfolding of a deep principle. The transition from unity to diversity, from symmetry to complexity, written into the fabric of reality itself. The concept of information also reshapes our understanding of creation. Increasingly, physicists are beginning to view the universe not only as matter and energy but as information. Every particle, every quantum state, every interaction encodes data about the world. If this perspective is correct, then the spark of creation was not merely the birth of physical stuff, it was the birth of information itself. This view ties into the idea of holography, where the information contained in a region of space may be described by data encoded on its boundary. Applied to the cosmos, this suggests that the universe could be understood as a vast hologram, with three-dimensional reality emerging from information stored in lower dimensions. If so, then the spark may have been the sudden projection of information into a new form of existence. Such a perspective also connects to black hole physics. Studies suggest that the information about what falls into a black hole is not lost, but preserved on its horizon. If true, then information is the most fundamental currency of reality, never destroyed, only transformed. Perhaps the same principle applies to the beginning of the universe. The spark was the transformation of primordial information into the structure of space, time, and matter. If information lies at the root of reality, then the mystery of the first moment becomes a question not of physics alone but of logic and mathematics. The spark of creation would then represent the transition from potential information to realized information, the first act of cosmic computation that gave rise to everything we know. The mystery of creation also compels us to consider the possibility of a pre-universe state. If the spark marked the beginning of our universe, what, if anything, existed before? Some theories suggest that before has no meaning, the spark was the true beginning of time itself. Others imagine a deeper layer of reality, from which universes emerge like bubbles rising in an endless sea. One proposal is the quantum tunneling model. In quantum physics, particles can pass through barriers they should not be able to cross, due to the probabilistic nature of their existence. By analogy, our universe may have tunneled into being from a state of absolute nothingness, or from a deeper vacuum, without cause or precedent. The laws of quantum physics themselves would make this possible, blurring the boundary between existence and non-existence. Other models describe the pre-universe as a timeless realm of potential. In such a view, the spark was the transition from possibility to actuality, from abstract probability to concrete reality. The universe did not appear out of nothing in the literal sense, it emerged from a field of potentialities governed by timeless laws. If this is true, then the spark of creation was less an explosion and more a transformation, the unfolding of hidden reality into visible form. Our universe may not be the only one to emerge from such a realm, others may have formed before, and others may form after. In this sense, the spark was not unique, but one of many transitions in a reality far larger than we can imagine. The idea of multiple universes, or the multiverse, reshapes our perspective on the spark of creation. If countless universes exist, each with its own laws and constants, then our universe is just one outcome of a cosmic lottery. The spark we call the beginning may have been only a local event, the birth of one bubble among an infinite foam. Eternal inflation offers one way this could occur. In this model, inflation never ends everywhere at once. Instead, it continues indefinitely in some regions, while in others it stops, forming self-contained universes. The process repeats endlessly, creating a vast multiverse. Our universe, with its specific conditions and fine-tuned constants, is one such region. This vision explains why the laws of physics seem so delicately balanced. Out of an infinite variety of universes, only some will support structure and life. We find ourselves in one of these, not because it was chosen, but because only such universes can be observed. In this sense, the spark of creation is not special, but typical, a single flame in an eternal blaze. Critics argue that the multiverse is untestable, existing beyond our observational reach. But some believe subtle evidence could emerge. Collisions between bubble universes, for example, might leave imprints in the cosmic microwave background. If such anomalies are ever detected, they could confirm that our spark of creation was only one among many, embedded in a grander cosmic landscape. The possibility of multiple universes also invites deeper philosophical reflection. If universes can appear endlessly, then creation is not a singular act but a perpetual process. Reality itself may be generative, producing cosmos after cosmos, each with its own laws, geometries, and histories. In this framework, the spark of creation is not the beginning of everything, but a recurring feature of existence. This raises questions about meaning and uniqueness. Is our universe special, or simply one of countless variations? Does the existence of other universes diminish the significance of ours, or does it elevate it by placing us within a vast, living multiverse? The answers are not clear, but the questions themselves expand the scope of our inquiry. Some propose that universes may even give rise to new universes. Black holes, for example, could serve as seeds for creation. Within their depths, conditions may mirror those of the early universe. If each black hole spawns a new cosmos, then the multiverse could be a branching tree, with universes giving birth to offspring in endless succession. In such a picture, the spark of creation is not only the beginning of our universe but part of an ongoing cycle of cosmic fertility. Each spark begets others, weaving an endless network of realities. Our cosmos may be both parent and child, a link in a chain of creation stretching beyond imagination. The spark, then, is not singular but eternal, echoing across infinite realms of possibility. As our exploration of the spark of creation draws nearer to its limits, we find ourselves standing at the boundary between science and philosophy. The greatest theories of physics take us astonishingly close to the beginning, describing how space expanded, how matter formed, and how light first emerged. Yet when we try to grasp what sparked it all, what caused existence to ignite from nothing, or from potential, we face questions that defy complete resolution. Perhaps this is because our tools, powerful as they are, remain tied to the universe we inhabit. Our mathematics, experiments, and observations are all part of the cosmos that emerged after the spark. To understand what lay before, or what gave rise to, the universe may require a framework beyond anything we now possess. Still, the pursuit is not futile. Each discovery sharpens the mystery rather than dissolving it, revealing that creation was not random chaos but a structured unfolding. From the balance of forces to the presence of dark matter and dark energy, from the fine-tuning of constants to the arrow of time, every detail speaks of a beginning both delicate and profound. In this way, the spark of creation is not only a scientific puzzle, it is a reminder of wonder. The more we learn, the more extraordinary the universe becomes. And though we may never grasp the ultimate answer, the act of seeking it draws us closer to the truth, and closer to the mystery that gave rise to all things. The implications of the spark extend far beyond cosmology. To ask what ignited the universe is to ask what it means for something to exist at all. Why is there something rather than nothing? Why do the laws of physics take the form they do, and why do they give rise to a cosmos filled with light, matter, and structure? These are questions not only of science but of existence itself. Some philosophers and scientists suggest that existence may be inevitable, that nothing is unstable, and that reality must emerge in some form. Others propose that our universe is but one possibility in a vast landscape, and that asking why this one may have no deeper answer. Still others hold that the question itself reflects the limits of human thought, trying to impose causality and meaning where none apply. And yet, the spark of creation remains more than a riddle. It is the ultimate origin story, the cosmic prologue from which galaxies, stars, and life have all emerged. Even if its full explanation lies forever beyond us, the fact that it occurred, the fact that existence blossomed from silence into something as vast and magnificent as the universe, offers its own kind of answer. We are part of that answer. Every atom in our bodies was once forged in the heart of stars, stars that themselves were born from the processes set in motion at the spark. To reflect on the first moment of creation is also to reflect on the deep connection we share with the cosmos, written into its very beginning. In the end, the question, what sparked the first moment of creation, may remain unanswerable in the absolute sense. The spark could have been a quantum fluctuation, a phase transition in a higher dimensional vacuum, a cycle reborn from a previous cosmos, or the manifestation of timeless mathematical laws. It may have been a unique event or one of countless sparks in an infinite multiverse. It may even be that no explanation exists in terms we can understand, because the origin of existence is not contained within existence itself. But the search for the answer is itself a journey of immense value. Every step toward the beginning, every glimpse of the cosmic microwave background, every detection of gravitational waves, every refinement of theory, draws us closer to the frontier of knowledge. The spark of creation is not only about the birth of the universe, it is about the expansion of human curiosity and imagination. So we end not with certainty, but with awe. The first moment of creation remains shrouded in mystery, yet it has given rise to galaxies, stars, and the very questions we now ask. It has shaped the laws of nature, the passage of time, and the fabric of reality. To wonder about it is to honor the vastness of the cosmos and the depth of our own curiosity. And so, as our journey closes, we are reminded that the universe began not with silence, but with a spark whose light still shines in every star, whose echo still hums in the cosmic background, and whose mystery endures at the heart of existence itself. And though we may never fully know what ignited the first moment, we can look into the night sky and feel its resonance, knowing that everything we see, and everything we are, began with that single spark.